2C Changes in Matter, Physical Properties and Changes. 2.11 Physical Properties and Changes. Physical Properties. A physical property is anything about a substance or object that we can observe or measure without changing its chemical composition. These properties include color, density, hardness, crystal form, texture, and physical state. We use physical properties to help us identify substances, classify them, and most importantly, determine the best material to use for a given task. Some properties are useful for classifying only certain substances in a specified state. For example, hardness applies only to solids. Consider the diamond teeth on a well drill bit. Diamonds are extremely hard and don't quickly wear down when boring through rock. If we were to replace the diamonds with quartz crystals, the drill would quickly grind to a halt. Why do diamonds work better than quartz? They share several of the same physical properties. Both minerals are transparent. Both can have beautifully faceted shapes. Yet the industrial diamonds are between 8.5 and 16 times as hard as quartz, depending on which measurement scale you use. Diamond's physical property of hardness makes it ideal for drilling through rock. Physical changes. When we study the world around us, we see that matter is continuously changing. Some of the changes affect the shape or state of the material. Any change of the arrangement of the matter in a material or object is a physical change. A physical change alone can't result in a change of the material's chemical composition. Most kinds of matter on Earth occur in the solid, liquid, or gaseous state. Matter can change states, but it remains the same kind of matter. Water freezes into solid ice, but it is still water. Alcohol may evaporate into a gas, but it is still alcohol. You know that sugar can dissolve in water, but it is still sugar. The sugar molecules have not been broken down into atoms. Even though the ions that make up table salt separate in water as a salt solution, when the water evaporates, a physical change, the salt ions come together again to form the crystalline solid. And you can grind wood into sawdust, but the sawdust is still wood. These are all examples of physical changes. People use physical changes in all kinds of ways. For example, we produce much of our electrical energy by huge steam turbine generators located in electrical power plants. Physical changes in water power these huge machines. Heated water produces steam under high pressure. The steam flows through the turbine blades, and the turbines spin electrical generators. As thermal energy in the steam changes into mechanical energy to rotate the turbine, the steam cools and turns back into water. Pumps return the liquid water to the boiler to repeat the process. See Figure 2.23 on the next page. In another example, we make many of our metal hand tools using a die casting process. A furnace heats the solid metal until it melts, and then the liquid metal flows into a mold. As the metal cools, another physical change occurs. The metal solidifies. The worker breaks away the mold to release the solid metal tool. 2.12 Chemical Properties and Changes. Chemical Properties. We can use other characteristics besides physical properties to identify or classify matter. For instance, why does pouring liquid water on a fire extinguish it, but pouring liquid gasoline on the fire causes an explosion? We say that water is non-flammable, but gasoline is highly flammable. Liquid oil doesn't corrode metals, but protects them from corrosion. On the other hand, a liquid acid can eat metals away. Iron rusts in the presence of water vapor and oxygen, but stainless steel is rust-proof. We can learn of a material's chemical properties by observing how it acts and changes in the presence of other substances. Chemical changes. Materials can change from one kind of chemical substance into other kinds of chemical substances. We use this property of matter all the time. Such changes in matter are chemical changes. Any change in a substance that affects the kinds of atoms and/or the way they are bonded together is a chemical change. We often speak of a chemical change as a chemical reaction, since in many chemical changes, the substances react in obvious and energetic ways. Common chemical changes include burning of any kind of fuel, photosynthesis in plants, digestion in your stomach, and rusting or corrosion. The physical changes that occur in a conventional power plant begin with a chemical change as the coal, gas, or oil burns in the boiler. 213. Using properties of matter to solve problems. Can you think of a way to prevent the serious injury or death of a police officer by gunfire? You could enclose him in a military-style tank, but it would be hard to climb a stairway to a third-floor apartment in one. How about an armored suit? The military is working on these, but a usable one is still several decades in the future, and they are pretty bulky. One of the most obvious ways is to use body armor, like bulletproof vests. Police officer Ambrose wasn't wearing a bulletproof vest when he was killed. Bulletproof vests are often made of a substance called Kevlar. Kevlar is ideal for protective vests because of its physical properties of strength and flexibility. Strength means resistance to penetration by a bullet or knife. It is 5 times stronger than steel and is almost as strong as spider's silk, one of the strongest natural substances known. Its strength, a physical property, comes from its molecular structure. Kevlar is made of polymerized molecular chains, a chemical property. These molecules tangle together and are very hard to pull apart. Strands of Kevlar are spun together into flat yarns and then woven into a fabric. Typically, 7 layers of this fabric make up a bulletproof vest. Under normal circumstances, Kevlar is extremely strong, but it loses its strength when it gets wet or is exposed to ultraviolet light. Manufacturers coat Kevlar fabric with a protective substance as it is made into a vest. The lives of more than 3,000 law enforcement officers and an unknown number of soldiers have been saved by personal body armor since it was first introduced in the 1970s. 2.14 Conservation of matter. Physical and chemical changes occur around us all the time. In many changes, matter seems to disappear. Water evaporates and wood burns. In other changes, matter seems to appear out of nowhere. Frost forms on cold surfaces. Plants grow more leaves. Your little brother or sister gets bigger. The models of matter that the ancient philosophers held were unable to explain these changes. The pseudoscience of alchemy included the idea that mystical chance and the influence of talismans could result in changing matter or bringing new matter into existence. After many experiments during the 1700s and 1800s, scientists concluded that the quantity of matter remaining after a physical or chemical change was equal to the quantity of matter present before the change, even if their forms were greatly different. The particle model of matter helped scientists to realize that the total number of particles never changed. Scientists describe this important observation in the law of the conservation of matter. Scientists often state this law: matter can be neither created nor destroyed, but only changed from one form to another. 2.15 Nuclear changes. In physical and chemical changes, the kinds of atoms involved always remain the same. These kinds of changes involve whole atoms or molecules and their arrangements, but the atoms themselves remain unchanged. What kind of change, if any, can alter the identity of an atom? Since the number of protons in a nucleus determines the kind of atom, to change an atom would mean changing the number of protons. Other changes in the nucleus involve changing the number of neutrons or emitting or absorbing high-energy rays or particles. Physicists call such events nuclear changes. Nuclear changes also include processes where large nuclei split into smaller nuclei, or very small nuclei combine to form a larger nucleus. Any of these changes can result in totally different kinds of atoms. These reactions take place in nuclear power plants and nuclear bombs. Physicists believe that a continuous nuclear reaction produces the sun's energy.